Hello, welcome back. What we're going to do um, in this video is some of the kind of calculation-y part of this chi-square goodness of fit test. What we've done so far is we've set up the hypotheses, we've checked the assumptions, we've found the expected counts, and we can compare those with the observed counts to kind of see how much evidence there is for the alternative hypothesis. But instead of just kind of comparing them, uh, informally, what we really want to do is have a formal statistical test so we can say a little bit more precisely how much evidence we have that there's a preference for one of those starter Pokemon. And so our test statistic is going to be this chi-square value. And so what it's going to be is our observed count minus the expected count squared divided by the expected count. That's going to be repeated for each category in our data set. And so that's going to be repeated once for Bulbasaur, once for Charmander, once for Squirtle. And then we're going to add up those numbers together, and that's going to be our chi-square statistic. We're not deriving this because, again, this isn't theoretical stats, this is applied stats. But we are going to kind of reason through why this makes sense and reason through how we're going to get our p-value from this test. And so if the null hypothesis is true, then this is going to follow a chi-square distribution. And so we kind of have to talk a little bit about what the chi-square distribution is, since it's different from the normal distribution. So the normal distribution, remember we wrote in shorthand notation, was normal with a mean, which we denoted mu, and a standard deviation, which we denoted sigma. And so there were two different things that influenced what the shape and center were going to be of our normal distribution. For the chi-square distribution, it's actually a little bit simpler because the chi-square distribution just has one single parameter or one single thing that's going to influence its shape and its center. And that's called the degrees of freedom. And so the degrees of freedom is just something that influences the center and shape of the chi-square distribution. For our chi-square goodness of fit tests, the degrees of freedom is just the number of categories that we have in our variable minus 1. The picture here shows different chi-square distributions with different degrees of freedom. And so this first one, which is the solid line, has a degrees of freedom of 2. This green dashed line has degrees of freedom of 4, and then this dotted red line has degrees of freedom of 9. So we could just kind of get a general sense that as the degrees of freedom increase, the chi-square distribution gets shoved to the right a little bit, and it becomes more and more symmetric. And so it starts out for low degrees of freedom as being very right skewed, and then that skewness slowly will disappear as our degrees of freedom increases. It's nice to just get some intuition behind it. We'll end up using StatKey though to actually make these plots and find our p-values. What we do want to make note of is that evidence for the alternative hypothesis comes when our chi-square stat gets large. And so we could see that because if the observed count is really different from the expected count, then when we square this number, that's going to get bigger and bigger and bigger. And so on the other hand, if the observed count is really close to the expected count, then that kind of indicates less evidence for the alternative and more evidence for the null hypothesis. And so we just kind of want to have that intuition that as the observed counts get really different from the expected counts, just like we set up here, then that's going to drive up the chi-square stat, and so that's going to be more evidence for the alternative hypothesis. So that's all kind of written out on this handout. And so our p-value is still going to be calculated from values that agree with the alternative hypothesis as much or more than what we actually observed. And again, all that is assuming the null hypothesis is true. So when we're thinking about this chi-square stat, what that really means is that if we're looking for values that agree with the alternative hypothesis more than the chi-square stat that we actually observed, we're thinking about anything to the right, or anything larger than our observed chi-square stat would be more in favor of the alternative. Okay, so let's kind of see all of this in practice. So our chi-square stat for this Pokemon data, just based on the formula on this previous page, I'm going to grab each of the observed counts, so 13, 17, and 26. And then I'm just going to subtract what the expected count would be if the null hypothesis is true. So that's 18.67. Square all of those, divide each by the expected count, and then add them up at the end. And so let's kind of do these one by one. You're welcome to follow along or not, it's up to you. And so this first one gives me a 1.72. Charmanders gives me a 0.149, and Squirtles gives me a 2.8778. Our final chi-square stat is 4.75. And so now when we're finding this p-value, we want to draw the chi-square distribution assuming the null hypothesis is true. So I'm going to pretty much draw this because our degrees of freedom are 2. Let's see if I do it somewhat accurately, look like that kind of. And so our degrees of freedom are 3 minus 1, and I'm just recopying that curve on the previous page, or you can use StatKey, which we'll talk about next. And now we're back to kind of what we were doing before. And so I'm going to mark what we actually observed, so 4.75. I can shade the region that's going to represent the p-value, since we agreed that in favor of the alternative was going to be values more or on the right tail of our chi-square distribution. Then I'm just going to shade this region. And then we can just use StatKey to actually find this area to get our p-value. We'll pick up with that with the next video, and then kind of write a conclusion and talk a little bit more about what these three individual values kind of indicate to us about where a preference might lie if we find evidence for a preference in the first place. As always, definitely let me know if you have any questions about any of this.